All right, everybody, welcome back. Today what we're going to do is we are going to be talking about even, odd, and neither functions. Essentially, it's another way for us to describe polynomial functions. It's another characteristic that we can kind of take a look at. So the first function we're going to take a look at is f of x is equal to 2x to the third minus 8x. All right, so here's the graph here, and I plotted a couple key points. I want us to take a second and see if we can, see anything that stands out to us. Well, one of the things that should stand out to us is these points that are plotted are very similar to each other. We have a negative 1.15, and when I plug that into my function, I get out a positive 6.16. Now, if I plug in the opposite, a positive 1.15, I get the opposite out, a negative 6.16. If I plug in a negative 2, I get out a 0. If I plug in a positive 2, I get out a 0. So it seems a little bit strange, but the reason that is because 0 doesn't have any sign to it. It's not positive, it's not negative. So it would really help us if we focus on these two values. What happens is, if I were to plug in a positive or a negative, my output are going to be opposites of each other. And so it sounds a little bit strange, but this is what we call an odd function. And here's our definition of an odd function. If I have f of negative x, that should simplify to the opposite of our original function. So now what that means is if I take my original function, which is f of x, and I plug in a negative x where each of my x values should be, got a 2x to the third minus 8x. So if in place of each of my x's, I plug in a negative x, what I should do is get out my original function, but the opposite. And here's how that works. If I go ahead and simplify this, I've got negative x to the third power. A negative value to the third power is going to remain negative, and that's because a negative times a negative is a positive, times a negative again is a negative. So negative x to the third is going to give us negative x to the third, times 2 is a negative 2x to the third, and then we have a negative 8 and a negative x, which gives us a positive 8x. Now, if we take a look, this is actually the exact opposite of our original function, which was 2x to the third minus 8x. It is the exact opposite, and again, it is the opposite version. So just to show you that again, if I were to put a negative right here, that distributes in, I get a negative 2x to the third plus 8x. All right, so this tells me this is what we call an odd function. Now, if we look at the graph, we saw some interesting things. And those interesting idea that is very prevalent here is that each of these values can be reflected across the origin and will land on another value on our graph. So take negative 2 and I reflect it over the origin. We should end at another point, which we do. And so this kind of follows for everything. If we just jump to the other side, we will forever get points on the opposite end. So we say that odd functions are reflective across the origin. So it sounds strange, but the origin, remember, is just a part in the middle. So if you take a point and you reflect it over the origin, you should land on another point of our function. All right, so that is an odd function. That's what that means. And this is the real definition down here, that if I plug in a negative x, I should get out the opposite of my original function. Now, we've got another type of function, and that is something we're going to look at next. So g of x is equal to a negative 3x to the fourth plus 6x to the second minus 3. Now, I've got some key points here, and I didn't label them, but I can go ahead and do that now. I've got negative 1, 0, and I've got 1, 0. So I really just used 2 points here, but this one's going to be a little bit different than before. It is not just if we reflect across the origin. Now, it works if we use this point. However, if I were to take a point down here and reflect it across the origin, I don't get a point up here. So this tells me that this is not an odd function. So it's going to be something a little bit different. Now, if we look at this and look for similar patterns of reflection, hopefully we should see that I can reflect across my y-axis, and I see that each point is reflected across and would land on another point of our function. So here's what I mean. If I take this point and I were to reflect it over my y-axis, I get another point which is right about there, also on my function. So this one's a little bit different. This is what we call an even function. The definition here is if I plug in a negative x value, I get out my original. And here's why this is important on the graph. If I plug in 1, I get out 0. Well, that means if I plug in its negative version, I should get out the exact same thing. And that's something we can see in the graph here, but we could also see in the equation. So my equation here, I'm just going to copy this, make it a little bit easier this time. Now, using this definition, I can go ahead and find g of negative x. So I'm going to replace all of my x values with negative x's. And I get -3. Well, anything to an even power that's negative is going to become positive. So it just becomes a positive x to the 4th. And the same thing is going to be happening over here when I square a negative value. It just changes to positive. And now we didn't do anything with that 3, so it stays the same. So if you notice, these are the exact same values. I plugged in a negative and I got out the exact same function that I started with. And that is because of this definition right here. So this is an even function, which we can see from our graph because it is reflective over our y-axis. And then this is what we call an odd function because we can reflect each of these points over the origin and land on other points. So it really works for all of these. And we can see that there. No matter where I choose, I can reflect it over the origin and I will land on other points on my graph. And that definition can be seen in here because if I plug in a negative value, I should get the original value, but negative, which is what I can see there. So again, this one's a little bit more difficult to comprehend. It's just saying plugging in a negative x value will lead us to the opposite y value. So when I plug in a positive 1.15, I get out a negative 6.16. Well, this definition is saying, hey, if I plug in the negative version of that x, if I plug in a negative 1.15, I should get the opposite of this. And then the opposite of negative 6.16 is a positive 6.16. So we can really use this definition to take a look at both the graph and the equation. It is very easy for us to look at the graph and try to determine quickly, hey, is something going to be even, odd, or neither? Because it doesn't need to be even or odd. Now, looking at the equations isn't as easy, but it just takes a little bit of practice. So let's take a look at a couple examples here. I've got m of x is equal to x to the 3rd plus a 2x. Now, what I need to do is I need to take m of negative x. Here's the important part. If I get out the opposite of my original function, then that means it is going to be odd. If I plug it in and I get my original function, that means it is going to be even. And if I get neither of those things, the answer will be neither. So let's take a look and see what that looks like. M of negative x is going to be equal to negative x to the 3rd plus a 2 times negative x. So I end up with a negative x to the 3rd minus 2x. Well, if we look at this, this is opposite, this is opposite. So my entire function is opposite of the original, and therefore this is an odd function. What that tells us is if I were to look at the graph here, I would be able to reflect any point I wanted across my origin, which is right in the middle, and I would land on another point on our graph. Let's keep moving. So now I've got k of x is equal to x to the fourth power plus 3x squared plus 7. Let's do some green. So k of negative x. Again, same idea. If I get out the opposite of my original function, then it is odd. If I get out my original function, then it is even. And if I get out neither of those things, it is going to be odd. So I'm going to go ahead and start plugging it in. I've got a negative x to the fourth power plus 3 times negative x squared plus 7. Well, I end up with a negative to an even power is just a positive. For each of these, same value, same value, same and same, and then I didn't do anything to that number, that constant at the end, so it changes. This is the exact same function that I started with, so that tells me that I got this definition working for me, which means this is an even function. One more. Now I've got L of x here, and I have 4x to the third plus a 2x to the second minus 5. Let's do some red here. So L of negative x, we kind of should be through this at this point, but if I get out the opposite of L of x, then that means it is odd. If I get out the exact same thing as L of x, and that means it is even, or something in between would be neither. So I've got L of negative x is equal to 4 times a negative x to the third plus 2 times a negative x squared minus 5. Well, I've got a negative value to the third power, which means it's going to stay negative. So I have negative 4x to the third. Now over here, I've got a positive 2, and then I have a negative squared, which means it stays positive, and I didn't do anything to that 5. So we've got an opposite first term, the same second term, and the same third term. So what that means is this isn't quite the opposite of our original function, and it's definitely not the same as our original function. So we say that this is neither even or odd. And just to kind of give you an idea real quickly, remember even functions can be reflected over our y-axis, so I could take a point and reflect it over, and I would get another point on my graph. Odd functions are reflective across the origin. So if I take a point like this and I reflect it over, I get another point on my graph at all times. No matter where I am, if I reflect it over, I should land on another point, as long as we're reflecting to our origin. Now, a neither function would follow neither of those things. And here's what I mean by that. We could have something that looks like this. Now, if I were to fold it in half, if I were to reflect it across our y-axis here, we definitely do not get values reflecting on top of other points. Now, if I were to reflect across my x-axis, I don't get values there either. So here's what I mean. If I take this and I reflect it over my origin, I don't get a point down there. That's another way that I can tell from the graph that this is a neither function. All right, so even, odd, or neither functions, it's really just another way for us to describe key characteristics of our polynomials. Even if I can reflect over my y-axis and I can plug in a negative x and get the original equation out. And then odd functions are reflective across that origin, that middle value. And I plug in a negative x and I get out the exact opposite of my original functions. And then, of course, we've got neither. All right, so the really bright students here that are paying attention, you might notice a couple things. This is an even function. If you look at our exponents, they're all even. Even if we focus down here at the constant, this is technically an x to the 0 power. Mathematically, 4, 2, and 0 are all considered even. This is an even function. Now, if we look over here, 3 and 1 are both odd numbers. We look all the way down here. We've got 3, 2, and 0. Well, remember, the 0 here is technically even, so I've got an odd, even, even. I've got a combination, therefore it is neither. So we can really quickly determine if a function is going to be, a polynomial, is going to be even, odd, or neither by looking at the exponents. If all of the exponents are even, it is an even function. If all of them are odd, it is odd. And if we have a combination of even and odd, it is going to be a neither function. All right, but it is still going to be really important for us to remember these key characteristics. We've got an even function definition right there. And then I've got the odd function definition right there. You are going to have to show algebraically how you know a function is either odd or neither. All right, thank you for listening. If you have any questions or concerns, as always, leave them in the comment below, and I'll see you guys next time.